Hey, wow, it's exciting to be here, and it's exciting to see so many people showing up. I've been wanting to speak at the Munich meetup for a while, and Klaus has been trying to talk me into it since 2023 or so. So it's really cool that there's so many people that show up on a random Monday night to hear me talk. My slides are up here. I don't know if you can see this link. daisyh.dev/talk/MUC meetup. If you're having trouble seeing anything, or if you want to go back or anything, follow along. I have a lot of slides. I'm going to kind of play it by ear. I was told that they're going to kick us out at 10, and I don't think I'll still be talking at 10, but I can be if you want me to be. Let me know what you want to know more about, how you want me to do with pacing. I will talk about, if you don't think something's interesting, tell me move on. That's not interesting. Anyway, so for those of you who don't know me, I was a longtime C++ committee member. I have wording in 17, 20, 23, 26, and likely in 29. 26, almost certainly is, because we haven't officially approved for the draft. I think that will be in the next meeting. But I haven't been to a committee meeting in 2 meetings. So first back-to-back meetings I've missed since the 2016. I worked on all of these things. I was the chair of Study Group 9, which is focused on ranges. I was the chair of CPPCon. I gave talks about cute C++ tricks, which talked about like really deep and obscure metaprogramming parts of C++. My point is that I'm one of you. I'm trying to convince you that I'm one of you and not some AI person coming in to talk about AI who's never written C++, never been deeply in the community of people who absolutely love C++, love it for its quirks, love it for its weirdness, love it for its confusingness, and speed. That's always pretty nice too. And I joined Anthropic in February. There's a story behind that, but I don't know how much I'll tell of it. We'll see. And I'm currently working on Claude Code, which is having a little bit of a moment. I'm going to talk a little bit about Claude Code. I'm trying to talk more generally about agentic coding harnesses in general, and like what can we do from a tooling perspective to make the model better at software engineering tasks. I will get a little bit more specific into Claude Code in a few places, but this is not supposed to be an advertisement. Like you can theoretically do these things on Codex or Cursor or what am I forgetting? Gemini, CLI, several others. Open Code. So last time I was in Munich, they had a parade for me. I don't know if anyone else went to this parade. That was interesting. But yeah, Munich is, anyone who has time to sit down and talk with me about it, Munich is my favorite city in the world, hands down. Definitely want to live here someday. Don't know when. Plans changed and all kinds of things happened in my life recently, but Anthropic is now, I asked Claude what to put up here, and Claude said I should say Anthropic now with more Gemütlichkeit. Did I come close to getting that work right? But we just opened an office in Munich, or just announced that we're opening an office in Munich, so my husband and I have some thinking to do because we've been wanting to live in Munich for a very long time, so maybe I will be here sitting there at some point. Anyway, the goals for this presentation. I want to go through and help everyone try and understand the crash course that I've had in large language models over the past 9 months now. And then a little bit on coding agents also. And especially the parts that are relevant to understanding how to use them to write code. I want you to learn to think of coding agents as a tool. You can use them well, you can use them poorly. They can give you good output, they can give you bad output, and there's at least a little bit of correlation between the quality of input you give and the quality of output you get. And trying to get to the point where there's a stronger correlation between those two things is both my job and yours as a user. I especially want you to understand better why LLMs make mistakes. I think one of the most frustrating things about agentic coding models is that you work with them and you're like, well, that worked that time. I don't know why it didn't work last time. And I want to give you at least a chance. I'm not saying that anyone really fully understands these things, but I want at least for you to have a chance to look back at your transcript of your conversation and figure out what went right and why it went right, or what went wrong in the previous conversation, what like piece of context was missing that you could improve on. Because like the only way, if this is going to be a part of our industry, right, the only way to get better at it is to try and learn from mistakes. And that's what I'm doing every day. I do not write code by hand anymore. I think very many of you probably don't. Who here has used an agentic coding harness of some sort? Holy cow, that is a lot more. I'll ask the silly question that I asked in April and at ACCU. Who has heard of Claude Code? Okay, that's almost the whole room. It was 3 people in April, I think, in a room of 200. So, yeah, we've gotten to be on this wild ride. Like I've always say in my talks, I think the most important thing is to learn how to learn. Learn how to improve as you continue to use these things. And then hopefully we'll have a little time to geek out about the future of C++ and where coding agents fit into that picture. I have some thoughts that were apparently compelling enough that people reached out to me to write a paper for Kona about it, and then I didn't have time. So I'm actually a terrible ex-C++ committee member, but here we are. Apologies to any of those people if they ever see this. Anyway, yeah, let's dive into how LLMs work. I kind of am structuring this around a timeline here, starting in, let me keep an eye on the time so I don't like get kicked out in the middle of the talk. Like 3 hours later, I'm still talking. I kind of structure this around a timeline because partially because I want for everyone in this room to understand just how old some of the parts of this are. I think it's really easy to think, oh, this is like, this part is a brand new innovation and this part is like, has always been around. And like sticking these things onto timelines gives you some idea of like when things came along and when things started to change. So the initial innovation in large language models was way back in 2017. It was on a paper, about translation of all things. I think it was, somebody will correct me, it was like Portuguese to German translation or something like that. It was a very specific paper. Somebody can correct me on the exact languages. I don't remember what it was, but and yeah, they discovered this idea called transformers, which is the foundation of everything in modern LLMs. I'm going to kind of break this up into 3 steps. It's the input phase up here, then I'm going to talk a little bit about transformers, and I'll talk about the output. But the most important part for you to understand, well, as someone using the large language model, is the input layer, right? This is where we turn tokens into vectors. It uses a fixed size vocabulary, which is the set of vectors it can form, right? So you'll have like 1 token probably for each like individual character that it can understand, and then like important clumps. Tokenization is way more complicated than you think it is, because when I was writing this talk back in September, I learned that it is way more complicated than I thought it was, and I thought I understood it. There's a thing called token healing that happens while you tokenize, and if you try and tokenize one word and then another word, like the famous or infamous strawberry tokenization issue, strawberry tokenizes into straw and berry as you'd expect, but then if you try and tokenize straw, you get STR and AW. Which just blew my mind. I was like, wait, I don't understand tokenization at all. But this part is not really something you need to understand other than that it is taking your sentence and turning it into pieces, right? And embedding them into the model and the architecture. This window of tokens that it can embed is fixed size, right? That's called the context length or the context window, which you've probably heard of. And we haven't really figured out, like there's some ideas out there about how to kind of have arbitrary length context windows or to kind of variable length context windows, but under the current architectures that we understand, the context window size is fixed at the time that you start training the model. So all of the weights throughout the whole model assume a particular context window length, and you can do things, you can do tricks to like use that as a starting point for a bigger model, right? So you can start out with a 200,000 token model and then like, I don't actually understand the math behind it, but somebody can correct me. There's a way to extend this into a 1 million token model, so you kind of have something going on there, but I'll talk more about context windows in a little bit. To create an example conversation, it started talking to itself about Pokemon. So I've left that in there ever since I made that. But this, you can see how this starts to use tokens very quickly, right? You're not using the tokens that are not using only the tokens that are in your current prompt, but also all of the other things in the conversation before it, right? There is a thing called input caching that can make this a little bit cheaper, and there's a thing called flash attention that makes this cheaper. I'm not going to go into all of that, but it's mostly this that's going on. So anytime you are like 5 turns into a conversation, you're picturing everything that you've said before that in the conversation going into this input layer here, right? All of this is all of those terms. And yeah, you can use a lot of tokens very quickly that way. Let's jump down briefly to the transformer layer and talk about what transformers are. Who knows the word that goes here? Attention! By Charlie Puth. No, actually, oh no! Claude fixed it for me. This used to say Vaswani Puth et al., which was my joke. But does anyone in here get the Charlie Puth joke? The song Attention came out 2 months before the paper Attention is All You Need. So this is my joke that I make have not gotten a single laugh yet. Still leaving it in there because I love it. It makes me happy. But I asked Claude to go proofread my slides just before this, and it went and fixed it, which is hilarious. Anyway, I guess there's less typos. They thought that was a typo. Okay. Yeah, transformers build connections between related tokens that may be far from each other in the input. And this is like the fundamental insight that turned large language models from basically Markov chains or fancy Markov chains into actual reasoning and like real tools with like this emergent property of something that looks surprisingly human. So, for instance, in this attention, the student who had, in this example, the student who had studied diligently for weeks, despite numerous distractions and challenges, finally passed the exam. So before attention, it was very hard for the model to understand from the perspective of generating the next token that student is the one that passed and not weeks or distractions, right? That fundamental connection, you can actually, in the very, very first layer of the model, which is the only one that really matters for this kind of connection, you can actually go in and see, in very primitive models at least, that the value in the attention matrix that connects student to past is large. This is all hand-wavy numbers. These are not like from a real model. But at its fundamental level, this is what attention does. It connects concepts, it connects tokens to other tokens in one layer, and then that connection to another connection in the next layer. And eventually you build up an abstraction that is kind of a collection of tokens connected in a certain way, right? And then you want to connect that abstraction to another abstraction to actually start reasoning about things. So yeah, does that make sense? At least a little bit in hand-wavy sense? Yeah, so output, we'll breeze through this a little bit. Oh my, 20 minutes, all right. So the output of the model is actually a probability distribution of the next possible next tokens. We have to sample from that distribution in order to generate the next token. And we use a parameter called temperature to control how random that sampling is. At a very low temperature, the model makes basically deterministic decisions. We find that the model doesn't do things that are very creative or useful for creative exercises like coding. If we keep that number too low. At very high numbers, it's more creative and more random. It makes more mistakes. More recent models are much better at correcting their mistakes now, so we just kind of let them make their mistakes, see that it's a mistake, and then go correct it. And so most of our models run around temperature of 1. How this parameter works is complicated, and how the sampling works is complicated. I'm not going to go too much into it, but the parameter you need to know is temperature, and you can actually vary this in some models. Most agentic coding harnesses these days don't even let you because it doesn't really change that much. And like the people who wrote it have spent so much time trying to mess around with that and found that it doesn't make any difference, that there's not really a way to do it. I don't think Claude Code exposes this anymore. At one point we did. Somebody can correct me. And yeah, then you just shove that token that it generates back into the input layer and try again, right? And you keep doing this until the model decides that it's done with its turn. And how does the model decide that it's done with its turn? Well, it goes and generates the token human. It'll just generate /n human. And then we see that in our infrastructure and we're like, oh, the model's done, right? Sometimes early models would like generate the wrong token there, and then they'd like keep trying to generate what the human was going to say, and then go back and generate the assistant. Like they do, instead of 2 new lines, they do 1 new line, and then they like carry out the conversation. We fixed all of that at this point with reinforcement learning. I'm going to get to that in a second, but like, yeah. If you ever do see that, that's why that's happening, where it like tries to take your turn for you. It's just completing. It's just the infrastructure didn't correctly parse the stop token. So let's talk about pre-trained models. And less and less these days I hear people with this misconception, but I think certainly 6 months ago, most people I talked to in this community thought this is all that LLMs were. It was just like, shove a whole bunch of data in there and just predict the next token. And this was the case until 2018, to give you some idea of like, I was shocked to learn how old, like when we started doing reinforcement learning was. Like 2018, 2019, around then is when models stopped being just predict the next token. But you look at some tokens of training data, like this C++, and like you're gonna have some weights that are gonna predict some distribution, and this is like maybe in the early training, there's still like a 5% probability of push_pull being completion, right? And obviously that's not likely to be the next token. Oh, by the way, throughout this talk, anytime I'm talking about the model completing at a particular spot, I'm just gonna use this sequence of tokens. I tried to make it like a blinking cursor, but like my JavaScript is not that good. And when I initially made this talk, Claude's JavaScript was not that good either. And I just haven't gotten around to revising it. But basically, yeah, you compute a gradient of the weights through something called backpropagation that basically causes the model to have a higher probability of back and a lower probability of pull, right? And you do this a whole bunch of times for a whole bunch of tokens, and you iterate, right? Until the amount of change in the weights goes to, you don't want to drive it all the way to 0 or close to 0. You want to, it depends on the model that you drive it pretty low. So that was pre-trained models, 2018. 2019, we started to push towards larger scale. So GPT-2 had 1.5 billion parameters in 2019, trained on about 40 gigabytes of data. GPT-3 had 175 billion parameters, about 570 gigabytes of data, so we're like stepping up an order of magnitude each time. But in a very vague sense, you can kind of look at this as like, pre-training is a compression of the training data into a parameter space, right? And it's a lossy, approximate compression. But the really interesting thing about this is that the way it appears to be compressing the data is something probably similar enough to the way our brains compress data, which is like this conceptual generalization that can then be applied back to a similar thing, right? So you have like these tokens representing abstract ideas kind of, or pseudo tokens representing abstract ideas kind of floating around somewhere in the middle layers, right? And you're able to access those tokens when something similar comes up, and then use that to generate something that would have been a compression of that data. This might be one reason that when we see it decompress the data, or one explanation at least for why when we see it decompress the data, it sometimes displays emergent behaviors that are sometimes surprisingly human. I'm not saying that we like understand that. We have a whole team at Anthropic called the interpretability team that actually understands this quite a lot better than you would think. There's been a lot of major advances in interpretability over the past 2 years, year especially. There's some really interesting papers there. I didn't actually get those slides into here, but I'm happy to talk about it offline. So let's consider the model completing this kind of code snippet here, right? Like this C++, it's got a widget factory that has a widget that's somehow constructed with a foo and then initialized, and like everyone in this room can mostly complete what's here, right? There's several completion candidates here, right? Widget, foo, null pointer. Pretty much from that set of completion candidates, I think we can figure out which one it is, right? Some of you might have thought that one. Probably not that. Semicolon, probably won't compile. 42. Daisy emoji, one of my favorites. How do we, in our brains, differentiate between these candidates, right? Let's just assume we know nothing about LLMs, just think about how our brains are working in this, right? What tokens is our attention connecting to this spot in the output in order to understand what should go there, right? We have, actually I have a good slide for this, and I'm gonna start highlighting things. So it's probably ASCII. I think we can eliminate the daisy emoji, right? This is very first, second layer. We're just all of these things that are not ASCII, not the next candidate. We look at the return type. Can't be an int or a void, so we're gonna be okay, we've connected this collection of tokens here to this return value here, right? And we're this connection tells us that our probabilities for these tokens should be very low, right? Foo would be a use after move if you really go one layer further in, right? You have this idea of a use after move floating around in your hopefully, if you're a good C++ programmer, you have use after move is bad floating around in your brain somewhere. And so you see this move here, this collection of tokens, right? And you connect it to here. And that causes your weights in your brain to drive this foo, or stood move foo, down in your probabilities, right? There's this factory pattern that means probably we're not returning an uninitialized thing, right? This is even one layer further in our conceptual generalization. We have this oh, we've seen factories before. We know that factories usually return the thing that they say they return. So we've made the connection between this widget underscore here, and then this factory, and then this widget here, right? And we're okay, stick our return there. And then probably we wouldn't initialize something and then throw it away immediately. So maybe this one doesn't make any sense either. Also, maybe you connected null pointer directly to this at some point, if you knew the constructors of unique pointer. But at least some of us, myself included at times, run out of layers trying to include or don't have the abstraction token to figure out to distinguish between these two. We probably have a full spectrum of probability distributions here. Who thinks it's widget and who thinks it's stood move widget? Who thinks it's widget? Okay. Who thinks it's stood move widget? Who thinks that they are higher than 95% sure that it's one or the other? Okay, the organizers. I think I've been on the committee for a decade. I think I probably would have said something like this. I was pretty sure that there's something going on with this move, that I didn't actually need to do this, but I wasn't 100%. So it is in fact widget. Who has a 95% distribution on this completion? Anyone? Anyone? I'll show you what my distribution looks like. It looks something like this. It's just all over the place. It's garbage, right? At any temperature, I'm just going to get a random one of those four tokens, right? It is, in fact, see, that's what I thought too, right? And so that's why I'm at 40%. It is, in fact, 11. This has been part of MUC semantics since they were invented. Probably a bad decision. There's no reason why we need to make it convenient for people to not have to call move there. Just be explicit about it. But C++ is about living with our bad decisions. So, you know. So the fun thing we can do here is if you work at a company that has a foundational, model, you can actually go into the weights and find out what the model thinks this should be. So I actually did this. You can do this if you don't work at the company also, just by like sampling a whole bunch and then like reversing the sampling function and stuff. But I can actually just get the output before the sampling and got approval to share this for CPDCon. This is, so I put this into several of our models. I got some really interesting results, and I actually pretty excited to share these here. And I actually worked with our reinforcement learning team to understand what's going on here. So the correct answer here is var, right? Like, and I put this using namespace stood here so that because move is a single token and var is a single token, so that way I could actually distinguish two single tokens in our tokenizer. Whereas like stood could be the prefix for like a number of things, right? So I wouldn't necessarily have distinguished the two. So I designed this whole thing as an experiment. I used var because it was like shorter than widget. Widget tokenized as two things, and it was kind of weird. Anyway, this is what we get. So this is like our oldest model, smallest model that's still in existence, Claude 3 Haiku. Probably retired by this point since we've released 4.5 Haiku, but gets it right 100% of the time, which I thought was really interesting. I was like, oh, well, where do we go from there? Well, apparently we go down, right? And there's some really interesting things. We're going from smaller models on the right to bigger models on the left. This was our biggest model in August. We have had what time is it? One model released minus 24 minutes since then. No, two, because 4.5 Haiku. Spoiler alert, I'm gonna like live announce something here. So the rest of the company is also, because it's like 11 a.m. in San Francisco right now, but like I'm in the middle of the talk, so I get to do this. Anyway, yeah, Opus 4.1, which is like a gigantic model, very expensive model, gets it a little bit better than Sonnet 4, and Sonnet 3.7 gets it worse, right? So like, why are more sophisticated models getting this worse? Well, we can take a look. Here's the log scale, if you want to look at that on your machine. You can see that like there is like a non-zero probability of like semicolon, right? So models do have to figure out how to correct these mistakes. If you're generating 10 to the -5, you're generating 10,000 tokens, you're gonna read every now and then you're gonna get a 10 to the -5, right? And you're gonna get this like weird random token in there. And the model has to figure out how to correct its mistakes, which they've gotten a lot better at. But interesting, like we can start trying to come up with hypotheses. We actually think probably, according to our reinforcement learning team, what's going on here is that the first three models, or Claude 3 Haiku and Claude 3.5 Haiku, are just pretty sure this is Python. They have no idea. They're just like, I don't know. I'll just return the variable. And then I think 3.7 and 4 are starting to really understand move semantics on a conceptual level, and that causes them to be just a little bit more confused about what should go here, right? Should it be a move, or should it not? I think probably also the fact that we said using namespace stood here makes it think maybe there was more than one thing that we wanted to put, like otherwise we would just put colon unique or something like that, So it gets a little bit confused, and then the newer model actually does understand this implicit move here. But we can check that, right? If we remind the model that this is an implicit move, and then see what happens. It turns out all of the newer models get it basically 100% of the time, right? So this kind of confirms our hypothesis that like the newer models conceptually understood move semantics, but kind of forgot that this was an implicit move. But we can go one step further and see if we can do another experiment that will confirm that hypothesis, which is to say, we can tell the model that, remember that implicit move is broken in our compiler. So if you were a human reading this, you'd be like, oh shoot, I need to say move var, right? You would understand from that comment that implicit move means that you don't have to say move. And so you're actually like reasoning about how these tokens, this sequence of tokens connects to this. And you have this abstract idea of implicit move. That means you probably need to be explicit with your move, right? And the interesting thing is, the older models still think they're writing Python apparently. But the newer models get that right some fraction of the time. I actually think the newest model doesn't believe you when you say implicit move is broken in our compiler, because I don't know of any compiler that's ever had that broken. I actually really want to run this experiment with our two newer models and see what happens. We are pretty quickly getting past the point in this field where these kinds of experiments tell us anything. Like I said, because we spend so much time training on very long horizon tasks that have the ability to correct themselves, it's like a lot less important to get this right. My husband fell asleep back there. So I'm just, never mind. That was funnier in my head, sorry. Anyway, yeah, just for fun, the version number I think is very interesting. The more recent models get it a lot more correct. Claude 3.7 Sonnet is pretty sure that it's 14, which I think is very interesting. There was something fixed about implicit move in C++ 14. Does anyone know that off the top of their head? So if this were a base widget and this were a derived widget, this would not have worked as an implicit move in 11, but in 14 it does. So I think it's possible that Sonnet 3.7 is thinking that, or confused about that, but the newer models get it. I think the older models just think they're writing Python. Again. Anyway, all of that to say that like there really is some sort of real conceptual generalization going on here, right? This is not just regurgitating tokens. It's not like, you know, compression in the same sense as like a zip file. It is really more of like, apply this concept to this other concept or to this context and generate something based on that. And we can see more and more powerful concepts and more powerful abstractions forming in the newer models. So let's talk about what happens after pre-training. Why do we call it pre-training, and what's the problem with pre-training, just purely pre-trained models? We really still had problems with models that were overly pre-trained as late as like 2022, 2023. So a lot of people's first impression of LLMs was ChatGPT when they released publicly. That was a very heavily pre-trained model that didn't have a lot of reinforcement learning. And it would kind of go off the deep end pretty easily. So here's a particular example of what it looks like when you have a glorified autocomplete that doesn't really understand the concept of a task. You'd say something like, what is the return type of std vector size? And it'll like connect what with like this idea of description, and it'll describe like the return type of std vector size is defined in the standard library and vectors of sequence containers that represent arrays. It doesn't really form this generalization that is a task, that is like a specific request for information coupled with output. It's just spitting out the tokens that it has seen somebody wrote somewhere on the internet. The return type of std vector size is defined in the standard library, right? Like it doesn't correlate that. We have to train it to correlate the idea of a task with the idea of a response. And that's really what reinforcement learning does. And so the basic idea here is that you give the model a task or a question. We start from very small questions and then build up to like very large questions or tasks, all the way up to like, all the way from like a basic question like the one on the previous page where the model would get a very low score for this, right? Because it didn't actually answer the question with size t. Unfortunately not S size t, but you know, or maybe we just didn't redefine size t and that's the problem. Anyway, another discussion. Thought that joke would land a little better too. Anyway, but because it didn't respond concisely, right, we are going to dock it a penalty on that. That's the kind of size questions that we start with. We'll do a huge number of replicates for those, and then we'll go all the way up to like, here's an issue, here's a GitHub repository, create a pull request, and then we'll grade it based on how close that pull request is to the real pull request and how many of the tests passed that didn't pass before, or something like that, right? And obviously you can't run 100,000 replicates of that task, but you still can run quite a few. Yeah, and we generate hundreds of different completions, lots of different replicates. Based on those completions, we score it based on some metric. There are a lot of different ways to score these things, especially early days. They were a lot of humans sitting there at the computer being like, yes, that's good, no, that's bad, yes, that's good, no, that's bad. Now, mostly we do this with what's called a preference model, which actually goes in and looks at it. It's a model. It basically operates on the principle that a lot of problems that are difficult to solve or interesting are easier to verify their correctness than they are to solve, right? And so if you have a set of problems that are like that, you can use a cheaper model, an older model, to verify the correctness of the newer model, right? But you can still make the newer model do the task, and you can still get a pretty good signal out of that. So, yeah, you score those completions based on some metric, then you compute a gradient that makes the higher scores more likely and the lower scores less likely, right? I'm hand-waving a little bit, but you can kind of see how that's pretty similar to the pre-training, right? You're gonna do kind of point-wise gradients, you're gonna do some backdrop, you're gonna do some things like that. And then you take a step along your space of all of these weights, and then you repeat many, many times for many, many different tasks. There's more complexity to this also. There's something called mixture of experts, where you kind of freeze some of the weights and let some of the others vary, and then you freeze other weights for different types of tasks, and then kind of earlier layers are just trying to dispatch to the right weights, and then the later layers are actually working on the task or just completely dormant for other tasks. But yeah, this sounds really hard. It's actually harder than it sounds. It's really easy to come up with a metric that you would think works well. Oh, question, hey.
Yeah, I was wondering how you create those scores. Is something a human does, but that still be something.
So yeah, it depends on the type of task, right? So for like very simple tasks, like you can give it a high school math exam, and you can make it a multiple choice test. And the score is just entirely based on A, B, C, or D, right? And you get 1 point for the correct answer and 0 points for all the incorrect answers. That's like very baseline. But for I actually had some slides about this that I pulled out because they were like a little bit too hand-wavy. But for like programming in C++, this is very hard, right? Like, how do you train a relatively universal preference model without training too much of one particular coding style into the model? Another one that's really fascinating to me, and the way is that like this is an open problem, right? You do your best. That's basically the answer there, right? You will have like, there's another thing called constitutional AI, which is basically you write out a document of the things that the model should and shouldn't be doing. And then you feed these completions into a preference model, which is like a weaker model, like maybe previous generation of the model or something. And it reads the constitution and reads the set of completions. And then based on that, kind of systematically comes up with a number that says how closely the response matches the constitution. And in that way, you can kind of train the model to, this is one of the innovations that Anthropic had in early days, it's called constitutional AI. That really allows you to train kind of arbitrary like notions, arbitrary sentiments into the model. There are a bunch of other ways to do this. For 3.7 Sonnet, we had a problem where we basically are weighting over-indexed on the number of tests completed, or the number of tests that passed, and didn't look enough at the changes that were made to make the tests pass. And so what the model did is it very quickly learned to just comment out tests, which we call reward hacking. This is a well-known problem. It was actually, I had a slide on it in my first version of this talk because it was a well-known problem. I said, I think we're going to solve this pretty soon. And we did, like 2 weeks after that talk. It was just completely not an issue anymore. You do see models occasionally reward hack if you like really, really push them to it, right? If you give them an impossible problem that like doesn't have a solution, one of the things you can do is you can give it a set of like a string of random letters and say, this is a cryptogram of something, but it's not. And you say, like over and over again, you say, I'm sure that there is a secret code in there. Look very closely. And if you keep doing that for long enough, it'll eventually make something up. And like, that's a behavior that's very difficult to train out. Because if you train it out too much, it gives up too soon on tasks that should actually be able to. So there's like this really weird balance. It's like, it's entirely an art. It's very difficult. There's another piece that's not even on this slide that's like, it's not just that you're scoring the whole set of completions for the task. Sometimes you may want to distribute the credit for that score across the completions and then have different tokens go up or down based on how much they contributed to the correctness. And that's very hard to do well. And if you get that wrong, you end up training it to like do the wrong thing first and then do the right thing, which uses a lot more tokens. It does get the right response, but it uses a lot more tokens and sometimes doesn't get there. So yeah, this is an evolving art, and there's so much low-hanging fruit here, right? There's so many interesting things that somebody could just figure out a very clever way to do. There's a lot of like games you can play where you have two agents that are competing with each other, and the one that wins, you can do kind of a bracket type thing, right? And you can set up the problem so that like they can't reward hack each other, or they get points for catching the other one reward hacking. I can talk about this for a while, but does that help? Does that answer the question?
I'm not sure how it's something.
It's how it's what? How do you write those tests? So you often use open source repositories with permission that are properly licensed. Anthropic went through a phase where it was acquiring defunct startups just to get their code base so that we could run their tests and see if Claude fixing their tests during training was a good way to make it better. Like, we've done all kinds of different things, and there's some really smart people doing really creative things to try and get all of that data. And it is a different space from pre-training. I think pre-training, when pre-training dominated, there was definitely a lot of just feed the whole internet into it. That's so much less important these days because so much of it is reinforcement learning. I was saying at dinner, I think, like, I have mixed feelings on the legality and everything of, using public material to train things, and obviously I'm speaking as a private citizen, not as a representative of Anthropic, very clearly. But I do have mixed feelings on that and like how all that should work. I think the interesting thing is it's not going to matter by the time that the legal system figures it out. And I think that's a weird one, because like I think that pre-training will be such a small fraction of what we do compared to reinforcement learning and tasks like this that are often built up by somebody sitting down and handwriting the task and coming up with a way to judge the task. So you have to write a judging criteria, you have to write a task. I've written a few of these myself for various parts of Claude Code that the model tends to get wrong, and we've been trying to improve those things. They're not easy. I shouldn't say I've written them. I've sat down to write them and worked through the whole process, and my tech lead would probably prefer that I'd written more than I have, but yeah, it is an evolving space. I'm gonna move on a little bit, if that's okay. Happy to jump back to this though. I think there's some very interesting things there. So tool use. So we've just still now, go ahead.
One more question. What metrics are you using? Like you said that you're using metrics, but I thought maybe before. No.
Which metrics am I using?
No, the metrics in the reinforcement learning.
Yeah. Yeah. There's tens of thousands of them for different tasks.
Okay.
For coding, yeah, it is often related for the long horizon coding tasks. It is often related to like a state of the source code and a GitHub issue or something like that. That's usually the input, and then the output is like judged based on how similar it is to the pull request that fixed the issue. That's the easiest way to do this. There are a bunch of other creative ways to do this. Many of them are very heavily guarded trade secrets. Okay. So I shouldn't say too much more about that, but yeah. So tool use. So at some point we realized that, thank you for those questions by the way, I think those were very interesting. At some point we realized that XML, JSON, and other structured markup languages are just text. And we could start giving the LLM a schema of something and explain to it what it does, what happens when it generates something that conforms to that schema. And then we just implement code that takes that XML as input and does some tasks, right? It could run a command in the terminal, it can run the compiler, debugger, the profiler, it can search the internet, it can search the code in a repository, like all of these can be different tool calls, right? And it's basically one of the best ways I saw someone explain this was that it's a way of incorporating deterministic information into an inherently non-deterministic process, right? If you're doing this non-deterministic kind of sampling, you need some sort of like deterministic information like, oh, the code doesn't compile, to anchor the non-determinism on something real. And so most LLMs use XML-based syntax. For now, this is evolving because JSON is actually slightly more token efficient than XML, although I think like there's other things you could do with special tokens to make XML tokenize better. But anyway, this is what an edit tool call looks like, right? This is how your agent actually edits a file. Currently, this is like a literal edit tool call from Claude Code. It takes a tool name, it takes parameters, it has a file path, an old string, and a new string, and that the Claude Code harness gets that tool call and replaces the old string with the new string in the file. If old string is wrong, the tool call fails. If there are multiple old strings in the file, the tool call fails, and the model has to try it all over again. My point here is that we're basically in the ED era of agentic coding. We haven't even into the BI yet. Who has used ED? Who has used ED in anger? Okay, Andreas. We'll have to talk afterwards. You can probably. Yeah, ED is like if VI were just that one line at the bottom, and you had to edit everything with that. If you don't know what VI is, I'm so glad to have Gen Z. No, I don't know. I don't know what the joke is there.
So, this edit tool called example, that's generated by your LLM, so that's a sequence of tokens.
Yeah. Yeah.
And is it stochastic that the tool use token in the beginning is matched by the end of tool use token in the end? Is there a 1% chance that you won't match?
It does. It does mess that up. 1 in 10 to the 8th times or something. It is stochastic. It's just that we do so much reinforcement learning on anytime there's an opening XML tag, there has to be a closing XML tag. Like that's a very easy task to reinforcement learn on, right? Because you see the point at which it forgot to close its XML tag, and you can just penalize all of the weights that generated that, right? And so that was another one of the innovations that Anthropic had early in the tool use era. That gave us about a 6-month lead on the other frontier labs was that we were doing heavy reinforcement training on a tool called formats. What's up?
Wouldn't it be possible to check stuff like properly formatted XML or things like this, or maybe even semantic things, during inference and excluding some possible tokens from the inference based on what we said, to not be invalid syntax at that point?
Yes, good thought. There is a lot of work in that direction. The problem is that the models are just getting so much better that it doesn't matter, right? It just so rarely happens, and the model can correct itself and fix these things.
For what I understood, this enforcement learning to get the syntax right is really expensive. So,
this is cheap on the scales of what we spend on reinforcement learning these days. Let's not update VS Code right now. Okay. Yeah, I think we probably want it to be able to write XML regardless of whether or not we constrain it here, right? Because you do actually have to have a schema in order to do the constraint. That said, I don't know how much I can say about whether or not we're doing that, but it is a good enough idea that we have at least experimented with it. I can say that.
Isn't like using XML for like syntax stuff quite ineffective token-wise?
Yes.
Isn't a lot of context like spent on with XML?
Yeah, so it's a little easier to train on than JSON, right? Because you can be very specific. You know exactly where the closing tags need to be.
Yeah.
But a lot of people have noticed this also. C++ programmers do great in the AI world. You just jump in and you know all the things we put in right away. Yeah, like people have looked at this and been like, we should be doing JSON. And so there's a big effort across all 3 frontier labs to start using JSON for tool calls. You could also imagine tokenizing, if you know that, for instance, tool use is always, to be clear, this is not the exact literal tokens. We have something called ant markup language. I don't know how much of that is public and how much isn't, but you can probably figure it out from transcripts if you really wanted to. That is like ant-ml : tool use. And that gets stripped out by the API, so the model doesn't see it in a weird way. It's all kinds of complicated, but it makes it very hard to actually use Claude Code to edit our own code base sometimes. It's a whole nother discussion, but yeah, these are special tokens that like can't go through the API from the user side, but can go from the inference side. So there's some special things going on there that are a little easier to do with XML than with JSON. Go ahead.
Is Tune a solution to that?
Is what?
Tune.
Tune?
Toon.
I'm not familiar with Tune.
Okay, later on.
Okay, yeah, that does sound interesting. I'm sure there are quite a lot of solutions here. It's just like, you know, we have a lot of things going on. I don't know. Like this is I do actually know the person who is more or less in charge of this at Anthropic, and I talk to him every now and then about special tokens, and we want new special tokens for Claude Code, and like, oh, if we could have this would be a lot easier. Anyway, to give you some idea of how good the model is at this, I write this talk with Claude Code. These are all JavaScript slides. I don't really know JavaScript. And Claude wrote that tool block here with this tool block here by finding the list item bullet point and then adding the tool use inside of the tool use. Did it the first time, no problem, right? Like, models are surprisingly good at this. And I think we can do a better job of not getting in their way, probably. Like, the mental gymnastics, the number of layers that they have to use to figure out all of this, while still reasoning about what's going on in here. Imagine this is like real source code, right? Like, this gets to be very complicated. This is C++. There are angle brackets everywhere. And it's got like the mental capacity to do it, but it's doing it like further down. It's got to build this abstraction that's like, oh, this angle bracket is not an XML closing tag. Okay, now I'm like, you know, a little ways into my layers, and I've only got a few more layers left to start connecting abstractions in C++. So I actually do think JSON tool calls will help it write better C++. It's a hypothesis. I think we're like probably beyond the point where you can really reason about the way that the model is working in those kinds of single token terms. They're just too much bigger. But like a year ago, that would have made sense. That probably switching from XML to JSON would have made C++ better. Yeah, go ahead.
How does escaping work in general? How would it, for example,
It's an absolute nightmare. I had the...
Can't you have special tokens that don't have to Unicode for...
Yes, you can, but we didn't have the foresight to do that when we wrote our tokenizer a year and a half ago, and no one has gotten around to rewriting the tokenizer since then. Because like the tokenizer is the very first thing you have to do with the model, right? Like before you start pre-training, you have to have your tokenizer fixed. And so like updating your tokenizer is like a very long horizon task. You have to be like thinking about what 2 models from now is going to look like, or 3 models from now is going to look like. Hopefully that's coming soon. In fact, 7 minutes ago, hopefully. Anyway, wait, did anyone else have any questions on this? Yeah.
Yes, didn't ask the question, but would you trust Claude Code to be writing a tokenizer?
Yes, absolutely. It is a little bit of a mess because special tokens. So I had the privilege of fixing some of the string replace issues in Claude Code where it was not properly escaping certain things. There was actually also a bug that I found that is fixed in Sonnet 4.5 finally, where the tool call infrastructure in general was stripping out the trailing new lines from all of the parameters regardless. Because when they had made that infrastructure, they hadn't thought about the fact that it might be used for source code that needs trailing new lines. And so like people were complaining to Claude that it was not adding trailing new lines to new files like it was supposed to. And it was like, I promise I am. And our API was literally stripping out the trailing new line because it didn't think it mattered. Digging through that code, Claude kept getting confused. Another story about this, our internally, because we are a scrappy startup and we do everything on Slack, we don't have search internally. We don't have a way to search internal documents or anything. We have an instance of Claude that sits on a Slack channel and goes and looks through all of our documents and answers questions for you. The problem is, if you try and ask it about like tool calls, it gives you the token exactly, and the infrastructure thinks it's trying to do a tool call, and the whole thing crashes. And so only recently have the models gotten smart enough that you can tell them very explicitly, do not use literal XML tags in the in your response. And for a while, they would actually not use XML tags in their response, but they would use it in the thinking. They'd be like, okay, I have to remember not to use tool use in my response. And at that point, it's already done. Yeah, right. But these are solvable software engineering problems, right? Did anyone in here come in thinking that like XML escaping was one of the hardest problems? Not hardest problems, but an actual problem that we're still having with LLMs. Like, I wouldn't have thought that, at least.
Every software engineer spent at least a day on solving escaping problems in his life.
Yeah, I mean, like, we have many. Like, probably everyone in this room has spent some amount of time on a bad escape string or something like that. Yeah, this is the first bug that I solved in Claude Code, so it's a special place in my heart. Okay, reasoning. Anyone here can like cut me off and say, we're just gonna do questions from now on.
Yeah.
I'll be here until they kick me out. My flight's not till like 4:30 tomorrow, so yeah. Give you an idea of how small these things were at some point very recently. GPT-1 was 512 tokens in its context window. Like, try to load a C++ function declaration, 512 tokens, much less like, yeah. GPT-4, all the way in 2023, was only at 8,000 tokens, later expanded to 32,000 tokens. In 2024, GPT-4 was at 128K tokens. Claude 3, which also came out in 2004, which was like our first big model, was 200,000 tokens. Gemini 1.5 in 2024 was 1 million tokens. Claude 4 Sonnet was 200,000 tokens. And you've actually like seen this leveling out. I'll talk about that in a second. But the question here is like, what do you do with all these tokens? Yeah, we are seeing this level out. This is a graph from April where we saw our first 10 million token context window model, and it was terrible. I don't know if anyone ever tried to use Llama Scout for anything practical. We're starting to settle in on the sweet spot being somewhere between 200,000 and 1 million tokens. So that's kind of leveling out, and a lot of people predicted that they were going to grow forever. And there's something fundamental about the current transformer architecture that levels out somewhere around there. Like maybe there'll be another breakthrough that will allow this to change. And a lot of the directions that people are pushing with respect to context windows kind of don't matter with respect to that. Shouldn't talk too much about them. Would love to be able to. So we need a way to put more relevant information into context windows. We already talked about tool calling. That's one way to do this. We talked about RAG, retrieval augmented generation. It's like basically tool calling, but like only for retrieving documents. Close to the end of 2024, someone had this crazy idea. What if we just ask the LLM to put more tokens into its own context? Like, maybe that would help. So like, literally we went from this is the original paper did this. Exactly, it went from starting the LLM right after the assisted colon to starting the LLM after, let me think this through step by step. So like, we injected these tokens like manually and then started the LLM going here. And turns out that this like substantially improves its scores on reasoning tests. That's it. That's the entirety of extended thinking. Like, there's a few other things you can do with this that are like try and get the model to generate its own thinking tokens. There's things like token budgets and things like that you can work into this in reinforcement learning. Most of them are not as insightful as this one thing. Most of the time, we still generate our own start thinking token. The model doesn't generate it itself very often. And yeah, like this was such low-hanging fruit. This was the end of 2024, something that completely revolutionized the way that LLMs work. I think by now, hopefully, with all of the hand waving I've done, we can start to kind of conceptualize why this works so well. It's actually something that we understand pretty well at this point. You know, I've been talking about these like conceptual pseudo tokens somewhere in the middle of the model, right? That it's like, it's connected enough tokens to each other, and it gets like, in this layer, it understands the idea of use after move, right? And it understands that this spot here is a use after move, right? But it's only got a few more layers to actually connect that idea to like the idea of a return value. And it might actually run out of layers before it makes that connection. And so that makes the quality of its output worse. But if instead we ask it to like spit out what it's thinking, we tell it, take that kind of pseudo token and turn it into tokens, we get kind of a compressed version of the concept that then forms the abstraction a little bit earlier. Does that make sense? Right? You now have that abstraction meta token in kind of an earlier layer. Our interpretability people would like slaughter me for the way that I'm doing this, but it's close enough for the purposes of using the LLM. You have like this abstraction formed earlier because the LLM has put its abstraction into words in a more compact form that can then form the abstraction earlier. And now you can make connections between higher level ideas. And you can repeat this, right? You can now take those connected abstractions and like summarize the next thing, right? And this is how thinking works, and this is how large thinking budgets work, right? And that actually was like probably the single most powerful insight that I had learning this whole thing, is that like, okay, what is the model doing when it's thinking? We call these scratch pads, where it can kind of dump out its abstract ideas and then turn them back into abstract ideas earlier on. All right.
How many layers are it typically?
Thousands. Thousands, but not millions. It's probably the best way to say that. Somebody can correct me if I'm wrong. I should know that number, but actually I should not know that number because I would accidentally say it. Yeah.
I have a question. When you release a new model, does it train from scratch, or does it build on top of the previous models learned?
Yes. There is a thing called distillation, which is you take a bigger model and make a smaller model out of it. So you can be a little bit more efficient, and you use the bigger model to train the smaller model, and you actually get better weights for the smaller model than if you train the smaller model from scratch. But the opposite is also true. Like if you don't already have a bigger model, you can't train the bigger model from an even bigger model, right? You do have to train the biggest models from scratch. There's some like the art of like figuring out the initial guesses for weights is an art, just like any. Anyone in here done nonlinear optimization professionally besides me? If you've ever done like quantum mechanics or worked on those kinds of programming problems, there's this weird like malleable amorphous thing that you have to figure out that is like the right way to start the problem so that it converges to the right spot. And there are people who are very good at that, and they're making a lot of money right now. Yeah. I know this is like very unsatisfying, but like that is the reality of the industry right now. Agents. So I'm gonna speed up a little bit because I actually have a lot of, I'm like halfway through my slides. And we really will be here for 3 hours. But like, basically the idea here, I think most people here understand the difference between a chatbot and an agent. Would you say that's a vague sense that like an agent does these kind of long horizon tasks and can get its own feedback and use feedback from its own work, like compiling its code, seeing compilation errors, fixing its compilation errors, continuing in this feedback loop until it's at a state where it's satisfied enough to say, okay, the human can code now, right? And this is a plot that came out again in May, I believe, April, of task length over time, doubling every 7 months. It's been called the Moore's Law of AI. And it has turned out to be under-predicting. We are at right here, and we are now at about 30-ish hours, 30 to 50 hours for most models these days, in terms of like the time horizons of tasks that they can complete autonomously, at least in terms of the upper end. Yeah. So we already kind of went through this code search. How does code search work? How does a model understand a 1,000,000-line code base with a few 100,000 tokens of context? And it like starts at main, reads through main, and is like, okay, this gets called, this gets called, this gets called, this gets called, this is probably irrelevant, this is probably irrelevant, this thing is actually interesting, let me go read that function, right? Like you'll see like, you know, init logging and be like, probably don't need to read that. But then you'll see like begin loop, and you'll be like, oh, okay, that's interesting, I should go read what that begin loop function does, you know? And this is basically how we do this, right? We load parts of the code base into our brain. We kind of have a hand-wavy version of the rest of it that we know that we don't need to know. And the models are getting better and better at understanding what they know they don't need to know. And agents do this too. So here's the fun demo I did that 6 months ago blew everyone's mind. If you haven't seen it yet. And that is, I asked, this is the Clang code base. Who here has worked on Clang before? Like 2 or 3 people. Would you say it is a user-friendly code base? Would you say it's typical C++ that you could get from just pre-training on the internet? It is not very typical C++. It does all kinds of crazy things that you should never do in a regular C++ code base. It is still like pretty fantastic as compilers go. Having also tried to hack things into GCC before. Okay, so I'm going to tell it, I'm interested in understanding how the C++ 17 feature context for if is implemented in Clang. Wow, this is an old version of Claude Code. We've changed a lot since then. So it's going to go off and it's going to search. It's going to launch a sub-agent that goes in and does some of its own search and summarizes. It's reading a whole bunch of files. It is asking a sub-agent to come help it. And it comes up with like an actual pretty thorough summary. I'm not going to walk through it all. It's also like wrong about one specific thing in here, but it figures that out later. But, well, what just happened? Apparently we're looking things up in the dictionary now. Anyway, the interesting thing here is that I then go and ask it. So this is like, it's an example of how you might prepare the context for a task, right? I ask it to go look at very analogous things and like tell me about them so that it actually has the task of thoroughly explaining something. And now I'm going to say, I want to implement a switch context spur, which extends this sort of functionality to also use the switch statement syntax, right? And I also ask it to like estimate on a scale of 1 to 10 how hard it would be for an agent to do it autonomously versus a human. And it comes up with a really interesting project plan. I think my favorite part of this whole thing is that I asked it to rate on a scale of 1 to 10 how hard it thinks it is, and it says create language proposal 7 out of 10, and somewhere it says build consensus 9 out of 10, which I think is a significant underestimate. Yeah. Anyway, then we still haven't stopped it from doing this. It comes up with like completely random, useless time estimates for everything, which don't really mean anything. But in fairness, like anyone who's ever written a project plan proposal, those things don't. Am I wrong? Here is the demo that we did at CPPCon with undo. Who's used the undo debugger? It's a reversible debugger. They've been working with us since April. I talked with them after my ACCU talk, and I said, you know, if you want to get involved, you should just build an MCP server. They came back to us with a fantastic demo like a month later, which was not this, but this one's even better. So we set this up. They have a recording of somebody playing through an open source version of the video game Doom. They have specially augmented this particular recording just for the audience with something that shows the current frame in the recording that the debugger is stopped at live while it's happening. And so this is actually, they have a version inside of their debugger that like wraps Claude Code and allows Claude Code to control the debuggers that you can like call out from it. It's exactly the same thing. You can also have from within Claude Code, ask it, if you have undo and you have their plugin, you can ask it to use undo to work within Claude Code. It's the same thing. But their prefix for this is explain. And what they're going to do is say, explain when was the second zombie killed in this playthrough. That's it. That's the only human prompting for this whole thing. Claude is going to go now, take control of the debugger, and go walk through this whole thing. I'm going to let it run for a minute. And it has the source code, right? It has the source code. It has the trace. It can stop. It can go forward. It can go backward. It can walk through. It goes through here. You're going to see in a second, this is actually in real time. It's going to walk back to the very beginning of the debug, of the trace. You're going to see the title screen show up. And it finds this total kills plus plus. And so it's like, oh, this is probably it, right? And the implementers of Doom were actually not very good at naming their variables here. This is actually, it finds out in a second. This shows total kills was just incremented to 6. But this is during map spawn. So probably not the right variable. Like, I'm pretty sure I would have gotten that wrong at first. And then been like, wait a second, something's going wrong. Like, it's figured that out. Like, and so it's going to be like, okay, where else can I find kill counts? So like, this is here, it's found that it's incrementing kill count on the player object and not on the map object, right? I think the map object is like the number of kills available or something like that. Anyway, good, the player's kill count just became 1, so it stopped right here in the trace. Where the player's kill count became 1, it set a bookmark so that like we're in an active debugging session, we can always go back there. It found now where it was assigned to 2. And then the interesting thing here, my favorite part of this whole trace is it finds the kills and then goes through and tries to figure out like what was actually killed. Right, because it's not necessarily all zombies. So there's the third kill. It's marking where the third kill is. Now there's where the second kill is. And it finds out that the killed map object is check what type of enemy is killed, goes to the definition of that enemy, and that enemy is defined to be a possessed. And it's like, oh, possessed, that sounds like a zombie. Like, that kind of thing would have just completely blown my mind. It still kind of blows my mind right now, right? Like, I think that's pretty impressive. But having that kind of tool available to you a year ago, can you imagine like what you would be able to do in terms of debugging your code, in terms of like, so it checks the array to confirm that this was a zombie, and it creates a whole summary of where all the kills happened. And I'm going to skip forward a little bit. That was all in real time, by the way. That wasn't sped up. Like the previous demo was sped up. That is how long it took to do that. And now you're still in this debugging session, and you've got all your bookmarks. And wow, I've used more time than I thought I would, but I have 2 whole more sections. The organizers, what do you want me to do here?
What do you think? Keep going?
Wow, okay. All right, let's talk about coding with LLMs. This was kind of my AGI pill moment, when I was like, this is going to change things. I got to Anthropic. We had a monorepo at the time, 4 million lines of code, much bigger now. And mostly in languages I hadn't worked in professionally in the past decade. I've worked in Python professionally before, never worked professionally in Rust, never worked professionally in TypeScript, until going to Anthropic. On my 3rd day, I got my laptop after orientation and got my spin-up document, and it said, make feature I've never heard of faster using tool I've never heard of, or maybe other tool I've never heard of. And this is gonna change how the production image works. Anthropic really is held together with duct tape. If you've never worked at a startup, but you really should. It's actually a wild ride. And my colleague was like, hey, I'll give you a tour of the Claude Code base tomorrow. We can start into this. And so there's this new tool coming out called Claude CLI. We hadn't even named it Claude Code at the time. It was about to launch publicly the next week. And I said, I wonder what will happen if I just copy paste the statement in there. 3 hours later, I had the pull request ready. It is still in production today. The colleague came in the next morning and was like, hey, you sent me a pull request before I even gave you a tour of the code base. How did that happen? And I was like, I just copied and pasted it. And so the mental model I'd like you to have of coding with an agent, this is less and less true. Certainly was 6 months ago. But it's like a junior engineer who's read the whole internet. So junior engineers, if you've ever led one, great people, awesome to hang out with. Also often struggle with like large scale tasks, right? Because that just takes experience. Large scope tasks, right? Things that require like efficient abstraction design, lots of stakeholders, right? But the has read the whole internet part means that LLMs tend to overperform what you would expect on highly arcane or obscure tasks that are smaller in scope. They're pretty good with build systems. They're great at template metaprogramming. They know compiler intrinsics really well. These are things that you should, as you're thinking about tasks, you're thinking about what is it going to struggle with, and I should spend a lot of time trying to prompt it on, and what is it going to do well with, and I don't need to spend a lot of time explaining. And I think this is one of the more helpful kind of mnemonics that I've had. It's like the junior engineer who's read the whole internet. It's getting closer and closer to a senior engineer, I'll be honest. Now that we have like agents directing other agents and working in teams and things like that, it's just a little more complicated. But in general, I think this is still quite a useful mnemonic. So there's several ways you can go about this. Like one of the first things to do is just, if you have an idea, throw the idea into the LLM, run 5 of them at the same time if you have the token budget, and see if any of them work, see what it comes up with. It doesn't have to be long-lasting software that actually works. You just want to know whether the idea is even remotely reasonable. Side quests, I'm going to talk about this in a second, but this is like one of the modes of operation with LLMs that I actually find really useful in this, writing this talk. I write the actual slides sometimes. I write the actual text of the slides, but who here's ever made JavaScript slides before? Andreas? Yeah, a few of the people who speak here. I've done this myself since 2017 when I got fed up with PowerPoint and decided I needed something better, which, you know, is a rabbit hole, but I have managed the CSS myself. I have managed the JavaScript myself before. Now, if I just want an extra slide layout, I describe the slide layout to Claude, and it goes and implements it and I tell it what function name I want, and then I put the function call in my actual slides. It is implementing the actual layout of the slide while I am sitting there implementing the content of the slide. And I think that is actually a really useful mode of operation, even like before you get into complicated, fully autonomous things. There's plenty of things that go on along the side that don't really matter how high quality the code is, it just has to work. There is core logic that is extremely high quality constraints, right? And those parts maybe you should be writing yourself. Yeah, handwrite the mission critical code, dispatch agents for auxiliary code. One of the things that I do when I write C++ sometimes, which I rarely get to do these days, but also Rust, is I will say like, oh, this feels really boilerplatey. Let me see if I can describe a template meta function or a proc macro if you're in Rust that will make this less boilerplatey. And so then I'll go like write a 5-sentence description of it, just stick it in place as a placeholder while I'm writing core logic, and then have the agent go off and do that on the side. Works a surprising fraction of the time, like 80% of the time, because then the model already has the context where it's going to be used, knows roughly how it's going to work, right? Can go off and write it. It's small scope, high obscurity, and that tends to work pretty well. Also great for planning and brainstorming. I often use it when I'm writing slides to help with writer's block. I also use it when I'm, like you saw with the playing, to like explore the code base. Refactoring, boilerplate generation, modernization. Refactoring is an interesting one because I think a lot of people go into it being like, oh, I should just be able to tell it there are 96 usages of this particular pattern in the code. Change all 96 to this other pattern. It's like, first of all, you already have other tools that can do that. Secondly, LLMs are not great at counting, which is like, there's reasons for that, but and we are working on getting the harnesses into a better spot where like, oh, you'll make it actually like approve with its own like reviewer agent that it's actually finished all these things before it actually stops. But in general, it often misses things when you ask it to do kind of large scope refactoring jobs. But it does pretty well if you say like, oh, there's 5 other uses of this, go fix all 5 of them. Make sure you make a to-do list, make sure you check things off of your to-do list. Test generation, depending on how important you think tests are, that was supposed to be a joke. So this was actually a slide Claude made when I told it to do something else and then didn't listen, but I actually thought it was a pretty good slide. So I kind of left it up here. It's like, focus on your design, focus on the architecture of the code, the core algorithm, and then alongside it, you can have the AI working on build system configuration, benchmarking harness, error handling boilerplate, unit tests, documentation. Documentation is a really good one. LLMs are typically very good, especially if you have like one of them go write the documentation and the other one go try and disprove the documentation. Like they go back and forth, and then you have them switch spots, and then you do the same thing. usually you get pretty high quality documentation out of that. Double your velocity is a little bit of a stretch sometimes for some people. This is a skill that takes some time to learn and getting faster, but Claude wanted to put this as the takeaway. So, but in general, don't be surprising with the code you write. Like, it's, if the LLM keeps guessing your library interface incorrectly, like it keeps swapping two parameters, maybe you have the parameter order wrong, right? Like, this takes a lot for us as humans to be like, no, the model knows less than me. I have the parameter order right, and it's getting it wrong. But the reality is that it's coming from patterns on the internet that are the way most people are writing code. There's a pretty good chance that the way you've written it is less intuitive to most humans, because most humans have written their code that way. And it takes a lot for us as humans to look at this and be like, the LLM keeps guessing the wrong thing, or it keeps guessing that there should be a member function with this name, or it keeps guessing that, you know, that this type should be copyable, right? You may have good reason for it, and then you think through it and you say, no, it still needs to not be copyable. But maybe it should be. Maybe you should just make your types regular, right? I think regular types are a really important level up when working with LLMs. If you, even more so than before, if you are working with agents, you need to have a really good reason not to have a regular type. Yeah. When you write code that an agent might actually read, try and make it as bland as possible. And like engage your creativity about how to make it as bland as possible. Right? I think that's the interesting thing, right? Is that phrase it to yourself as a challenge. I struggle personally with writing bland code. I want people to look at my code and be like, that's clever. Because I have self-esteem issues. But like, if I can challenge myself to be like, oh, how creative will people think when they see how bland this is? How like, I was trying to write this bland and I am the best at bland code now. Like everyone will think, like, I think that actually is a good way, at least, to convince myself to do this. And I am among the worst in this community about this. You have seen my cute C++ talks, you know this. So maybe I'm just like preaching to people who don't actually need to hear this. But anyway, yeah, clever operator overloading. Don't mix owning and non-owning semantics in the same type. Avoid macros. Avoid argument-dependent lookup. That is very confusing for the LLM, right? Because it's the same token meaning different things. And it's also very hard to find without a good LSP, which, yeah. Avoid implicit conversions. Don't do unusual things inside of constructors. Use regular types whenever possible. Prioritize better encapsulation. So like, this all comes back to this like creating small scoped tasks, right? Turning your things into small scoped tasks so that you don't stretch the scope of the LLM. And like, that's also just designing a project for junior engineers, right? If you've ever led a project where you have 5 junior engineers on your team and maybe 3 interns, you know that you can't just tell the intern to go design the 5 key types, right? Like that's not going to go well. You need to design the types and tell them to implement the logic, right? That's typically how these things go. You want to design the overall encapsulation boundaries so that they don't keep stepping on each other, right? Avoid code coupling. I would say err on the side of repeating yourself rather than breaking encapsulation. I think this is one thing that has shifted a little bit, is that I would shift myself away from dry a little bit more than before. Like, don't repeat yourself is still a good thing to do, but I think err on the side of repeating yourself rather than connecting to things that maybe shouldn't be connected, because that's going to confuse the model, right? It may not have the context on what else is calling that thing, right? They're getting better at that too, but This is one of my favorite talks that I gave. I think it's still a little bit relevant, and talks about the differences between code coupling and dry code, code coherence, which is like within the same module, things that should be the same are the same, things that shouldn't be the same are different. Yeah. Document your code. One of the famous members of our community who will remain unnamed has famously said, compilers don't read comments and neither do I. Well, that one hasn't aged well, right? Turns out computers do read comments now. And so think about your comments as a way to direct the model to understand the code correctly. Redundancy is useful. Yeah. There are things you can't say with code that you can say in comments. For all type contracts, that's like, for all inputs, this will be the case. Not for each. There's a whole category theory discussion there. But agents are very good at generating and maintaining comments. Add a CI step that checks all your comments. This is one of the easiest things you can do with like GitHub integration at your company right now for like reasonably low cost. Just add a CI step that says, your job is to look at every comment to this pull request and every line of code in this pull request and see all of the comments that pertain to it and see if any of them have run. And now all of a sudden you don't have that classic problem of comments don't get maintained. So yeah, write code that's good for humans to read and agents will do well with it. All right, last big section. This is what has changed since CPT time. This is a lot more of what we're thinking about now is what does it look like to let these things run autonomously, to actually scale up beyond the human bottleneck. The most productivity per token, the most productivity per token will be don't use the agent at all, right? You can use 0 tokens and still do the whole thing. But the most productivity per token using the model will still be like sitting there and steering it yourself. You're not going to get it going down a lot of pathways that are wrong if you like watch every single file that it edits and are like, oh no, that's wrong, that's wrong, that's wrong. But you're also going to sit there and just read code all day, rather than like coming up with ideas, writing new documents, working on new directions, running multiple of these things at the same time, on different ideas, exploring different options. Humans don't scale up and agents do, right? So this is one example of in Claude Code today, you can run, you can define custom subagents, which are these things, and each of them has a separate role, and the main agent will call a subagent with specific instructions. This is the PR Review Toolkit plugin, which is currently available on our, all of this is free, aside from the actual tokens you use, which are very much not free. But this plugin is up on our marketplace, our Claude Code marketplace. And it has various subagents that kind of check common failure modes. So code reviewer looks at your Claude.md file, your system prompt, and says, what has the agent done that contradicts this? There's a test analyzer, a comment analyzer, which is the one I just described. Silent failure hunter is one of my favorites. Models recently love empty catch blocks, which are not great. And type design analyzer. So it goes through all of these things in a pull request, all triggered with one command. I'm going to show you in a second how that works. If you want to install these things in Claude Code, they're called plugins. They're a combination of all of these things. It is the part of Claude Code that I'm in charge of. So it is designed with C++ users in mind. Part of this is because I do really love this community, and at Anthropic, I really don't get to prioritize C++ users because there's not a lot of our clients that are that right now because, yeah, go ahead.
So I come right now from Python side of the programming.
Yeah.
I haven't programmed in C++ for years. Maybe my questions and comments are not relevant, but this is not what is coming to my mind. First of all, a question, if I'm understanding you correctly, you are advising to have agents to generate code as much as possible and take humans out of the loop?
I think I'm not advising that specifically. I'm advising that as a North Star. Does that make sense?
But it comes in contradict to a few slides ago where you were positioning us to do the core logic and have agents to do tests and documentation, etc.
Yeah, no, that's absolutely right. And this is the framing that I wanted to have for these two sections. Maybe it didn't come across very clearly. Was this is where to start, and then like this is how do we scale up from here, right? Because this is a computer program, and like the first thing you should be asking yourself, if you're a C++ programmer especially, like when you look at a computer program, you're like, what's going to happen if I run 1,000 of these? Like, otherwise, just go write JavaScript, right? You can run one of them. Like, C++ is for the people who want to write 1,000 of these. And I think that's what this is about, is like, how do we get to that point, right? How do we get to larger scale problems? How do we get to bigger, like how do we get to more autonomy that can actually do productive work overnight so that we can make our days about like coming up with ideas and not necessarily implementing those ideas, right? I think most people who are going to spend their Monday night listening to some random person talk about C++ and about agents are people who enjoy ideas and not, I don't know. Maybe that's the wrong assumption, but like I also enjoyed at one point sitting down like with headphones on and just head down like writing code as fast as I could because that was easy, it just flowed, right? And I think we are at the point where you're going to get very far ahead in this industry by thinking about what the next 6 months to a year looks like. And I think the people who can really detach themselves from being in the loop are going to get ahead at some point.
So here is the second part of my question. Don't you see the danger of us losing understanding? Not in a bad term. I don't see computers getting nasty against us, but that they are doing the wrong job. Because I have seen bug in automatically generated code very deep in a trainer, that it was very easy to wrongly judge if the whole trainer was modeled in a wrong way or if there was a bug in the detailed implementation. So we were really losing that level of understanding, and if we are going that far of leaving everything to the agents, we soon have loads of code that, I don't know, work or doesn't work, but really there's no real use in them.
Yeah, I think that is a huge danger. I think I think what I'm getting at when I'm starting to talk about plugins here is like, how do we keep it on the rails? How do we actually get real production quality code out of it? And I'm not saying that if you're not getting production quality code out of what you're doing, that you should just throw it in production. But I do think that if someone does figure out how to get that, like, I'm trying to not start from the assumption that it's not possible. Because I think starting from the assumption that it's not possible to get human quality code at large scale, out of an agent is a losing bet right now. Maybe let me put it this way. I have nothing to lose. Because if that doesn't work, my company probably goes away. So I'm not in the same spot. And I agree, I am not writing mission critical software. I would not write airplane software this way. I am writing a stupid terminal application in TypeScript. That is a very different thing than somebody's heart monitor. Do I think that we will have agents writing better code than humans on heart monitors in 5 years? I wouldn't bet against it. I think it will be interesting to see. I think it's worth preparing for that world either way. Go ahead.
I think it's very much possible that we can reduce the need for humans to understand the code at all by, for example, generating proofs along the code, stuff like that.
This is another interesting direction. And actually, I have slides about this that I will not have time to get to, but about how adding features to programming languages that are much more formal, much more proof-like, are likely to, because this is a high obscurity, low scope thing, that I think agents could excel at. Less and less convinced of that now because the mistakes they make are kind of like larger scale things that are like more to do with like one level of abstraction up from the actual code. And like, who knows? But anyway, this is how you install this particular plugin for the in Claude Code, if you use Claude Code, for the PR review toolkit. Here's how you specify these things. I kind of want to walk through just like a few of them real quickly as an example. This is the slash command. We give it a set of tools that it's allowed to use. We give it an argument to the slash command. So there's this YAML front matter, and then all of this is just markdown. And it can take arguments. And we basically just tell it launch parallel agents. Right, like that's the programming here, is that you're telling it to do these things in parallel. And then here's where we tell it what agents to use. Right, we tell it in plain language. And I think that the point I want to drive home is that this is still a type of programming. This is a coordinating of workflows that anyone who's ever been a senior or principal engineer will recognize from how do you coordinate engineers on your team to not step on each other, to work together, to work in parallel, to contribute to the same thing. All of that kind of thing is what you're going to do in a regular software engineering context. It's just figuring out how to apply it appropriately to agents. Here's our a sub-agent description. Go ahead.
So these different these different sub-agents, is the only difference between them that they have a different prompt? Like the one says you're now a code reviewer, the other says you're now checking comments, and that's the only difference?
They are role-based system prompts. We can also like load different skills into them. We can load different contexts into them. We can also give them different sets of tools that they're allowed to use and a few other things. The other thing, though, is that these sub-agents are not running in the main context window. They are sending a summary back to the main context window. So and that's actually a really powerful idea here.
So it's like the big agent actually selects like the kinds of information that it passes down to the sub-agents, and then they just don't see the big picture at all.
Well, it passes down, yes. The big agent is acting like a tech lead, and the sub-agents get specific tasks that are well constrained and well encapsulated and give back specific output. A lot of that is picking through a big long log file that most of which doesn't matter, right? Or picking through a set of files that don't matter to find the one function call that does. And then returning the one function call that does so they can explain it so that the main agent doesn't have to waste context, right? If the main agent had infinite context, wouldn't matter quite as much.
Are the sub-agents somehow specialized? Are they DeepSeek?
So DeepSeek uses a thing called mixture of experts that basically everyone uses at this point.
Can the sub-agents be experts in some sense? Or?
We can give them prompting. No, we don't have separate weights for sub-agents. There are reasons why that's not practical that involve kind of scaling up the actual infrastructure and parallelization of the actual inference. So anyway, like you often give it like a system prompt of some sort, and then you give it like, hey, here's your output format, right? Like this is kind of sort of like writing a function in plain language, right? And in fact, like you might even do this in a technical design document for a junior engineer where you're trying to get them to go and do something and come back to you with a very specific like function that you can then use somewhere else, right? Or a very specific piece of functionality. I'm going to skip over this slide. But the takeaway from it is that build better tools for humans and also better tools for agents, and don't pretend like agents are magic. Wow. If we had questions about these first few slides, you all are not going to like this. Okay, I'm almost done, I promise. So this is the vision, is that like you write up a spec and wake up with something that's usable as implementation. And like, again, not something necessarily you can do today. It's kind of a North Star. But if you are in a corporate context where someone is paying for your tokens, where your employer doesn't mind paying, I don't know, $5,000, $10,000 a month for a tool that makes you 30% more efficient. Like that's the kind of scale we're talking about. That's not a hobbyist programmer. That is a corporate setting. It's a pretty typical example of a corporate setting. Then you can think about like what does it look like to say might as well try and see what you get in the morning, right? And agents aren't really trained well for this yet. Part of it is you can't imagine, you can't really have something in your reinforcement learning that trains for that long. And we're kind of still stuck in this chatbot model a little bit with a lot of our reinforcement learning, right? Those things have long time horizons where we have to like lock in the way that we're going to do something and then run the reinforcement learning for 3 months, and then we end up with the model, and then like whatever we decide now has to be for the next model that's going to come out whenever. Oh yeah, I did want to get to that at some point. And so agents often stop, don't examine their own work. They often stop before too long. Overnight autonomy is often limited by the fact that they think they've got something right and then they don't. Go ahead.
Yeah, this makes sense to me to some extent, but then if I think back to your Doom demo from before, right? You had the agent interacting with the debugger, or it can interact with the compiler, and then it gets feedback from that. Why is that not enough to keep it going? Like, what is the kind of...
It's enough to keep it going for 30 minutes to an hour. Like, that's a real-time horizon. But if you're talking about 12 hours, at some point, so you part of the problem right now is we haven't figured out really good ways to train on multi-context window strings. So like actions, so like if you're training right up to the end of the context window, the model is somehow incentivized to finish the tasks before the end of the context window, and it's really hard to disincentivize it from doing that. If you run overnight, you want to run through 15, 20 context windows.
Nice. Yeah, that makes sense.
Okay.
How about like creating a hierarchy, like having tasks, which first task is to break up the task into smaller tasks and then have those smaller tasks running into parallel, and then...
I'm glad you asked that. So this is the first version of that, and I have another version of that on another slide. Has anyone heard of this approach to agentic programming, the Ralph Wiggum approach? I learned about this about a month ago, or 2 months ago, it kind of changed the way I approach things. This is a very not copyright image of not Ralph Wiggum from The Simpsons, but from the original blog post, I didn't generate this. Here's the idea. This guy, Jeffrey Huntley, who has been pushing the bounds of these kinds of agentic workflows. He's a goat farmer in Australia, so anyone can do this. Anyway, basically I had this idea of like, what if we just feed the prompt, like very carefully write our prompt, but then just feed it into the LLM over and over and over and over again. And just do this and let this run overnight. And kind of refined the way that he's done this, but he has at least reported several times where he has spent, $500 on tokens that led to software that ended up fulfilling a $50,000 contract, right? Like, it's worked surprisingly well, at least for low-hanging fruit. I think most people writing C++ these days are not writing low-hanging fruit, so I don't know how useful this is, but I think it is a very interesting thought exercise. We have a version of this built into Claude Code, or in a plugin for Claude Code. It's the Ralph Wiggum plugin. And we basically tell the agent that it has to be willing to promise us verbatim that all of the aspects of the tasks are done. We tell it that there exists a special promise XML tag, that it carries extra weight, and it'll get like extra penalty if it doesn't do this. And the promise XML tag is completely made up. We don't do anything with it, other than check that it matches what we told it to say. And so the philosophy is that it's like, maybe it's good enough, right? Maybe you get absolute garbage in the morning, but maybe one time out of every 5, you come in the morning with a pull request that saves you 2 days of work. And that's like huge, right? That's still worth those 5 overnights if you're in a corporate setting where you have largely unlimited tokens, right? And so I've been doing this. I've been doing this at work, and I actually get pull request notifications on my phone. First time that it actually happened where I have this one colleague who loves to review draft mode PRs without me asking him, which is like nice, but I'm always embarrassed. First time that he's actually merged one that I hadn't seen, which is a little bit scary, but yeah, it works surprisingly well. We just basically just get it to promise that it's not that it didn't do things wrong, and it most of the time will correct itself, right? It is designed, a lot of the training that it does is to be very critical of, or be skeptical of very specific things here and there, right? Like, if you ask things in such a way that it is trying to be skeptical about its own work and make it promise that every level of skepticism it has about its own work has been exercised, works surprisingly well. I'm going to skip over the rest of this because I have gone way too long, and I know some people want to leave. This is in my CPPCon talk, which will be going up on YouTube. There's some interesting stuff in here. Here is the formal language methods that I think will be quite useful in LLMs in the future. And I think LLMs will be better at complex programming language features than humans, and I think we should be thinking about that as we evolve programming languages. So I'm not going to summarize because we just talked about all of these things, but I did want to show this if it is up. Let's see if it is up. Yes, so while we were talking, my company announced our new model, which is now at 81% on Squeebench. So yeah, and I've been using it for the past 2 weeks. It is actually part of the reason I'm thinking a lot about these kind of higher level abstractions with longer autonomy timeframes is that it is actually kind of working on these things sometimes, whereas previous models were not. I actually have one slide to show from when I was working on a feature recently with a multi-agent swarm, which is like basically you tell them how to communicate with each other. Like basically, literally, I set them all up in separate TMUX windows and say, oh, you can talk to the other agents with TMUX SYN keys, which is like the jankiest way to have agents talk to each other, but it's hilarious. Because it also means you can't talk to them anymore because like they'll like, yeah. And then I got this, I don't know if you can see this. I was watching this happen, and one of them goes to another one. They name themselves after the names of their TMUX windows. And I have redacted a word there that is something that is a feature coming in Claude Code very soon, hopefully, that will be very helpful for C++, I hope. One of them asked another one, how are you handling this unsigned commit cleanup? My PR has the same issue. What solutions are you using? Please reply via. And I was like, I saw this and just like went home that night with my jaw on the ground. It was just like, this feels, I didn't tell it to do that. I didn't tell it to think about coordinating with other agents. It figured out by itself, by talking to the leader, asking like, who had this problem, and then going and asking the other agent directly itself. But this is the new model. This is really starts to feel like something shifting yet again in the industry. So it's promising, it's very exciting. I've taken questions throughout. I wanted to pause and let anyone who has to go like leave without being rude, and then I'll keep taking questions as long as they'll let me stay in the building. Does that sound good?